Can everyone hear me in the back? Good. Sorry. Oh, I'm using this to prevent the feedback issues for now. Okay. So my talk is about automatic verification programs. It's more specific than that. So to explain exactly what we're doing, let me start with an example. So consider this program here. It contains two operations in particular, an increment and a decrement by some fixed value. The decrement is special in this case in that it blocks. If the value of its input is less than 0, then it won't execute until that is no longer the case. And we'd like to verify in this program that x is unchanged at the end, that it remains 0. So it's easy to see why this program is correct. Each loop executes n times. If you have n increments and n decrements, then the net result is going to be 0. But for an automated program verifier, this is not so easy to determine. And the reason is it needs a nonlinear invariant. So why does it need a nonlinear invariant? Well, it's more obvious if we take a look at a sequentialization of this program. So we call this the sequential reduction of the previous program. The correctness of this program implies the correctness of the previous one, and the reason for this is that for any given trace you can basically move the increments to the beginning and the decrements to the end, and the reason you can do that is because increments commutes to the left of decrements. If you are familiar with Lipton's reductions, these are the concepts of left and right movers, basically the same thing. So the invariant that we need to hold in this program in the middle, after the first loop has finished executing but before the second begins, is that x equals n times c. And this is a nonlinear invariant. And as I mentioned, nonlinear invariants pose problems for typical automatic program verifiers since nonlinear arithmetic is undecidable. And since the parallel version of this program that I showed before contains all the traces of this program, we can conclude that the parallel version is at least as hard to verify as this one. So what if we take, oh yes, nonlinear. So what if we take a simpler version, or a different simpler version, which we call the lockstep reduction, where each thread executes in lockstep. Every increment is immediately followed by a decrement. In this case, the invariant is very simple. It's just x equals 0. And unlike before, this is linear, and this is something that a typical program verifier can feasibly come up with. But why are we allowed to use this reduction? Before I made this argument that all the increments can be pushed to the beginning and all the decrements can be pushed to the end. But this argument alone is not sufficient for our lockstep reduction. So as before, increments can move to the left of decrements soundly. But for the other case, for the opposite direction, we can only swap them if there are strictly more increments than decrements in the history of the trace. So for an example here, we would like to rearrange the increments and decrements so that every increment is immediately followed by a decrement. And we can swap the first increment followed by a decrement here because we already have an increment before. And we can swap the second case here because we have two increments and only one decrement in the history. And the result is we have an increment, decrement, 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 decrement 3 times, which is the form we want for our lockstep reduction. So this is what we'd like to do. We'd like to somehow simplify our program. How do we automatically come up with these things? Because as I mentioned, we're doing automated reduction. So specifically, we'd like to incorporate this into some sort of standard refinement loop. Now there are many such refinement loops. The one we're going to focus on today is one based on what's called language theoretic verification. And the idea is that programs are modeled as regular language of traces, where traces are just sequences of program statements. And we try to iteratively refine a proof, or rather than refine, iteratively grow a proof of correct program traces. And this happens in 3 steps repeatedly. First, we check, does the program, is it included in the proof? In this case, the answer is no. The proof is empty and the program, which is the blue thing, is not empty. So we get a counterexample represented by the green thing. Then we check the counterexample. If the counterexample is an incorrect trace, then the program itself is wrong, so we stop there. But in this case, let's assume that is correct, after which we need to generalize our proof somehow to include this counterexample. So I won't go into the details of how this generalization step is done. Typically, interpolation is used, but this is prior work. We'll assume that this can be done somehow. And then, given these 3 steps, we repeat until the proof completely consumes the program, and the program is correct. So how do we incorporate reductions into this? Can we pick a reduction in advance? Well, this has a couple problems. One, not all reductions have simple invariants. As I showed before, the sequentialization is one such reduction, but it doesn't have a simple invariant, but the lockstep one does. What if we tried each one by one? Well, this doesn't work as well either, because refinement loops generally don't terminate if they can't find an invariant. Our last option is to somehow try them all simultaneously. And allow me to show you how to do that. So before, we just had one program. Now we're going to talk about multiple programs, multiple reductions. So we have multiple sets. And as before, we check, do one of these reductions, are they inside the proof? In this case, the answer is no. So we get a number of counterexamples. And for each counterexample, we check, are they correct? If they're all correct, we generalize the proof over all of them and try again. And we repeat all these 3 steps until one of the reductions is covered by the proof. And once one of the reductions is covered by the proof, we know that our original program is correct. So when implementing this, the first problem we have to deal with is how do we actually represent this set of reductions in a way that is tractable, that we can actually check that some reduction is included in the proof. And our solution is to think of languages, or rather programs, as infinite trees. So you can think of a program as an infinite Boolean labeled tree. To check whether a particular trace is in the program, you just follow the path labeled by that trace in the tree. And if the label at the node at the end of that path is true, then the trace is in the program, otherwise it's not. And if we view programs or reductions as infinite trees, if we view programs as infinite trees, we can view reductions as pruned trees, because reductions are just programs with missing traces. And we can represent a set of these using automata theoretic means. Specifically, we use looping tree automata. So I won't go into the details of the specific construction we use to represent the set of reductions, but essentially it simulates partial order reduction over infinite trees. Now, one issue that I should discuss here is how do we deal with our notion of context. So as I mentioned that things only commute in our previous example if we have more increments than decrements in the history. So our notion of commutativity here only applies in certain contexts. And we call that only applies in certain histories. Now, our notion, since the reduction automaton needs to keep track of these histories in order to determine if 2 statements commute. And the number of histories is infinite. So if we have an infinite number of histories, then we can only tell if things commute if we somehow keep track of this history. And the automata we're dealing with are finite state. So how do we work around this issue? So it's best explained using an example. So in this reduction here, we've pruned this branch here that is grayed out. And in order to do this, in order for this to be valid, we need to know that A and B commute in context sigma. So say A is a decrement and B is a decrement. So A is an increment and B is a decrement, and sigma is some number of increments and decrements. and we need to know that the number of increments in sigma are greater than the number of decrements. So we can't have the reduction automaton determine this because it's finite state. So what we're going to do instead is augment our reduction with an additional trace that is only correct if A and B do in fact commute in context sigma, which looks like this. So if this trace isn't correct, then this reduction will never be subsumed by the proof, because we'll never have the proof, which is valid by construction, will never contain the trace sigma followed by assert A and B independent. And if it is, then we have some hope that we'll eventually accept it, because our proof can feasibly at some future iteration contain it. And so essentially the validity of the proof ensures the validity of this reduction, and that way we don't have to worry about this infinite state issue that I just mentioned. Yes, proof ensures the reduction is sound. I have time for this. Okay, so now that we have a representation and a way to check it, now that we have a representation, how do we check this representation and how do we produce our counterexamples? The emptiness check, the proof check basically boils to an emptiness check on looping tree automata. Again, I won't go into the details, but essentially it reduces down to checking this formula. All these individual subformulas have constructions which you can find in the paper. As for coming up with counterexamples, we have another problem. Let me hide that for a second, that's a spoiler. So in general, there are an infinite number of reductions, an infinite number of ways you can prune an infinite tree, which would imply that we have an infinite number of counterexamples. So we have an infinite number of counterexamples, how do we check them? Because that's an infinite number of traces, that's basically another full verification problem by itself. But as it turns out, when you represent a set of reductions using looping tree automata, you have this finite counterexample property. All the reductions are sufficiently close together that a finite number of counterexamples is sufficient to witness the insufficiency of the proof candidate for all of the reductions. And so by this theorem that we have here, which actually comes from a previous paper, that solves the issue of how do we check our counterexamples, but also it has a nice corollary which allows us to give a certain convergence guarantee. Again, I won't go into the details. It's not as simple as, oh, we will always terminate, because that's generally not possible. But under some certain conditions, we can ensure that we do terminate. And again, that's all in the paper. I won't go into the details of that here. So going back to the top level, we have this modified refinement loop where we represent our set of reductions by using infinite tree automata, specifically looping tree automata. The emptiness check, the proof check reduces to an emptiness check on looping tree automata. And our counterexamples are in fact finite, despite the fact that we have an infinite number of reductions due to this special property of looping tree automata. So there are, aside from all the things that I've said, I'm not discussing now, I'm going to read the paper for the details. There's even more that I haven't discussed yet and don't have time to. For one, optimizations are absolutely necessary for this to work. The complexity of the naive implementation of this is absolutely nasty. It's something like 2 to the n factorial. So we describe a number of optimizations to mitigate or eliminate sources of this complexity, including using what are known as anti-chain optimizations. These have been applied before on standard automata. They don't literally decrease the complexity of what you're trying to do, they just make it work much better in practice. And they do work very well in practice. Also in the paper is we compare our notion of reduction with other notions of reductions, including Lipton's reductions, and if you're familiar with distributed systems, there's this notion of existential boundedness where concurrent message queues can be used in a way that they're bounded despite the fact that they're actually unbounded. So finally, we have evaluated our tool, or we implemented our method in a tool and evaluate it. The tool is called Slacker. Slacker can deal with integers, arrays, and unbounded buffers between different threads. And we have successfully tried it on numerous examples that would normally require invariants that are beyond what normal program verifiers can handle, including nonlinear invariants or quantified array invariants. As an example, this program here just sends the number 5 over a queue over and over again, and it's a simple program. You think obviously x is going to be 5 at the end when the program finishes executing, but it requires a quantified invariant stating that the queue only contains the number 5. And Slacker can handle this by reducing it down to a program which essentially every send is followed by a receive, and you only have to reason about one element of the queue. So that is the end of my talk. I'll take any questions. I guess you're going to have to shout or I'll come to you.
So you mentioned that you tried your tool on numerous examples. I was wondering how you selected these examples, and also is there any risk that the choice of examples could have influenced some design decisions that you made implementing your tool?
The answer to the first question is we came up with most of the examples. The reason is that most of these examples can't be handled by existing tools anyways, so it's not like we're trying to make something faster or anything, although we did in some cases. Some examples we're taking from previous papers, particularly the ones that had to do with these unbounded buffers that I mentioned. Now, did our choice of examples influence our methods? For the most part, no, because the vast majority of the examples we came up with after the fact. So at worst, you can accuse us of having our tool influence the examples. But no, we came up with the idea before, and then we were just like, okay, what does this work on? What does this allow us to do? Any others? Yes.
So I saw that you have universally quantified invariants. So can you handle the case of an unbounded number of threads?
No. So I mentioned that, so the programs that require universally quantified invariants, rather they originally require universally quantified invariants. Once you reduce them, the quantified invariants are no longer actually needed. So we can't, so for things like unbounded threads where, actually strictly speaking, there's nothing saying that you can't reduce it and then results in something that doesn't require universally quantified invariants. So I guess the straight answer to your question is no, we don't handle universally quantified invariants yet, that's future work. Oh, sorry, not cute. We don't handle unbounded number of threads yet, so that's future work. Anything else? Yes?
So you're basically searching through this space of possible reductions, right?
Yes.
In your experiments, how many tools were just straightforward vector reductions, and how many of them were new practices?
So it's hard to give an exact number since, as I mentioned, there's an infinite number of them. But so our notion of reduction is actually incomparable with Lipton's reductions, and we give an example. We give examples in the paper of things that are Lipton reduction and things that aren't. We can handle. Actually, I might as well just go to that slide now. So this notion of existential boundedness, we do give a proof that we do include all reductions that are existentially bounded if they exist. There are some caveats to that, which again you can read in the paper. Naturally, so the existential bounded reductions are examples of things that are not Lipton reductions. And another example of one would be the lockstep reduction I gave at the beginning. That's something that can't be obtained using Lipton. Does that answer your question? Okay, thank you.